Good afternoon, one and all. Today we are going to look at unit number 2, which is gate level modeling. We have seen the basics of the gate level modeling in the previous classes. Now let us look at a more detailed discussion about gate level modeling. Okay, so the first and foremost important thing is that everybody knows that all the digital circuits are constructed by the basic gates. Everybody knows this one. But we can say that all the basic, sorry, all the digital circuits constructed by basic gates. Clear? So if you take any digital circuit, for example, so all these all these digital circuits are constructed mostly by using the basic gates. Of course, 100% that is a basic gates. That is the lowest level of abstraction. Now, these basic gates are available as a primitives in Verilog. Okay, what we can say that these basic gates are available as primitives. Very important word is called primitive. Primitives in Verilog. Okay, I'll also remove this one. I'll use another color. Basic gate. Okay, what do you mean by a primitive? So that means a primitive are generally modules. This is also a module. Whatever the basic gate is there, that will be considered as a module. The definition of the module is already existed in the Verilog library. Clear? What we can say that? Primitives or generalized modules that already exist in Verilog IEEE standard library. Okay, as soon as whenever you are using the Verilog library, normally we don't show the library related information while you are writing the Verilog program, but default there is a work library is there in that library. Yeah, these basic gates are available. Okay, that means the definition of these basic gates are available in the library. That's what you have to remember. Okay. So what are the different basic gates that are available in the library? That's what we should know. Okay. So what are the basic gates? Generally, we have to use AND gate, or I can say that available basic gates used in Verilog HTL. What are those? Let us consider one thing is AND gate. We have to use small letters only. Okay, if you want to write an AND gate in your program, you have to use small letters A and AND. OR means ORR, that I should write small letters only. NAND means NA and NAND. NOR means NOR gate that we have to write. Okay, XOR. XOR, no, I'm sorry, it's not XOR. XOR is something like this. XOR or XOR, XNOR. Okay. What are the another thing? NAND gate, sorry, not gate, buffer. So buffer also people will know that, buffer. So these are the basic gates that are available in Verilog HDL. Okay. Of course, these are more than sufficient to construct any digital circuit. Is it clear to all of you? Fine. Now, how do we use these gates in your program? Okay, fine. So that means that we should know what is the syntax of this one. Syntax of using basic gates. Right? How do we use this one? For example, I'm going to consider an AND gate. Okay. We consider an AND gate. For example, A and end I'm going to write. Okay, so it is an optional. G1 is actually optional. Optional, we will write it by using the green color. The gate is G1, for example. Okay, now I'm going to write, first I have to write output signals. Output, I should write output, and then input 1, input 2, input 3, so on up to input n. Input n. After this statement, semicolon we have to use. So this is how we have to use gate statement or gate primitive statement. What we normally call this is, it is called gate primitive statement. Don't forget this word. Okay, so this is the syntax that we have to use in gate level modeling, right? So that means that let us consider a simple gate. What is the size of this gate that I have written here? So what is the size of the gate? It is actually n input AND gate I have written. Okay, that means that this is the gate. This is an AND gate having input 1, 2, 3, 1 up to an input. So therefore this is called input 1. This is called input 2. This is called input 3. Sorry, input n. Okay, this is output. So what it says that if you are writing any AND gate primitive, that means a primitive means this module definition is already there in the library. Therefore, how they have defined that one, they have mentioned only single output and n number of input can be possible to use. Okay, so according to your requirement that you can use. For example, if you want to use 2 input AND gate, for example, 2 input AND gate, then what I can do it now, and for example, this is the gate number 2, for example. So only two inputs only I'm going to consider, input, output, and then input 1, comma, input 2. Okay, so that is how I can write. So what it says that it is a 2 input AND gate. It is actually a 2 input AND gate. Clear? So these are the primitives that we have. This is how we have to use the primitive statements in Verilog HDL. Okay, is it clear to all of you? So only, so instead of the AND gate, you can use OR gate, XOR gate, XNOR gate, AND gate. Okay, so many things that we can use. But if you want to describe a circuit in the gate level modeling, these are the gate primitive statements that we have to use. Okay, and let us consider how, when we are using these kind of gates in your program, what is the truth table of this gate? Okay, so let us write what the truth table of these gates. Okay, for example, let us write here is truth table. truth table. Let us consider only one particular gate, and that is similar to the all other gates as well. Okay, everybody knows that. Everybody knows that. For example, if you consider an input, two input and a gate I'm considering. Okay, so for example, A is my input, B is my input, Y is my output. Okay, how do I write program for this one? So I'm going to write in this way. A and the end I need to write. The name of this gate is, for example, G1. G1 I can write. G1 I can write. It is G1. So the variables I'm using here is y comma output I need to write first, and then input and another input. Okay, so this is the statement that I should write. So please remember, A and B can be interchangeable. That means instead of first, if you want to write first A, first B, then you can write B and also, or I can say here I can write it in this way. So I'm writing as a comment something like this. If I'm writing that one, it become a comment. Both are equivalent, and this is end G1. It is nothing but y comma b comma a. So there is no difference between these two statements. So what is the difference I have done? First, b I have written is the one input, a is another input. Okay, so the simulator will identify, or the synthesis tool will identify that first one is a output signal, and then b and a are the input signals. Okay, but we should not write first b then followed by y followed by a. It's not acceptable. Okay, but it is wrong. For example, I'll write in this way: gate and g1 b comma y comma a. So for according to your notation, y you are treating as an output signal. So but if you're writing something like this, it is not wrong actually, but it is taking b as an output signal, y and a are the input signals. Okay, so logically there is no problem. The syntax orientation, it does not have any problem. When you are executing this one, logical error that you will get it there. Because in our circuit diagram, we have B is an input, but you have written as an output. You have written as an output signal. So therefore, it will give you logical error. But syntactically, there is a correct. It doesn't know that whether B is an input signal, Y is an input. It doesn't know that unless otherwise you specify as an input or output signal, right? So please be careful about while we are writing all these things. Okay, so this is not at all acceptable. Okay, so this is acceptable, this is acceptable. Fine. Now, the question is that how do we frame the truth table for this one? Everybody knows that whenever we are writing and indicate something like this, input A, B, for example, A is input, B is an input, Y is my output. So we know that what is the possible combination for the A and B? Can anybody knows that? What is the possible combination? We know that the possible combination is 0, 0, 0, 1, 1, 0, 1, 1. We are expecting like this only. And for that one, we are getting 0, 0, 0, 1 is an output signal. Fine. So this is what we normally considered for an AND gate output, right? This is the AND gate truth table. But in Verilog point of view, okay, but in Verilog point of view, it's different. In Verilog, what we say that, so whatever the gate that you consider, okay, so whatever the gate that you are considering here, A, B, Y, A, B, Y, okay. So as everybody knows that it can accept not only the logic 0, it is not only the logic 0, it can accept logic 1 also. Everybody knows that. Of course, it's a binary number system. Therefore, each and every line or each and every variable is valued with either the logic 0 or logic 1 or the combination of logic 0 and 1. But in Verilog point of view, each and every line can be treated as a 4-valued logic. Not only 0 and 1, there may be a possibility of unknown value, there may be a possibility of high impedance state. Similarly, for this one also, this may assign by logic 0, or it may assign by logic 1, or it may assign by logic X, or it may assign by logic Z. right? That means each and every variable or each and every line in your digital circuit in Verilog point of view will take 4 possible values for each and every line. ఓకే సో ఒక లైన్కి 4 పాసిబిలిటీస్ ఉన్నాయంటే అట్లాంటి 2 లైన్స్ ఉన్నాయి అనుకోండి ఎన్ని పాసిబిలిటీస్ వస్తాయి మనకి హౌ మెనీ పాసిబిలిటీస్ దెన్ విల్ హ్యావ్ as I mentioned in the previous classes here is it is accepting only logic 0 and logic 1. Here is also it is accepting logic 0 and logic 1. So the number system is actually a binary number system. Therefore 2 things that we are considering because only 2 digits only we are considering to give the value for any line, right? That is the reason why it is 2 only. So how many such lines are there? 2 lines, A and B. Therefore, we have to put power is 2. Therefore, we have 4 possibilities. So that's why it is a possibility number 1, possibility number 2, 3, number 4, right? Similarly, what about here? What about here? How many possibilities that we can have? So how many, what is the number system? It is a quaternary number system. This is a 4 digits that we are using. We have to consider the 4. How many such lines are there? 2 lines are there. Therefore, this one is 4 power 2. That is 16 possible combinations we need to write. Okay. So therefore, whenever we are writing the 4 possible combinations, people will try to write like this in this way. A, B, okay. And Y we can write here. So how do we write this one? Therefore 0, 0, 0, 0, 1, 0, X, 0, Z. Okay, we need to write something like this. We need to write, right? Is it clear to all of you? 1, 0, 1, 1, 1x, 1z. So another possibility is that x0, x1, xx, xz. Another possibility is that, what is another possibility? z0, z1, z2, zx, zz, right? So this is the possibility. Okay, then what is the output that we should know? So we already know that for this combination we know, for this combination we know, for this combination we know. We don't know what is the values of other things. Now we define its truth table in a more compact form. Okay, let's write in a more compact form. So let us write here. So the input, for example, A is an input here. For example, here is the B input here. Here is the A input I'm going to write. Okay. So this is for one value. This is for another value. This is for another value. Okay. This is one value, second value, third value. Okay. So what I'm going to write here is that if input A can be 0, input A can be 1, input A can be X, input A can be Z. Similarly, input B can be 0, input B can be 1, input B can be X, input B can be Z, right? Now I need to fill this one. Okay. So everybody knows that. So the simplest way of understanding the AND gate is, everybody knows that if any one of the input is equal to, see, the brief or compact form, or brief, or I can say that compact way. Compact form is, for example, if you consider and indicate something like this, from this truth table we can easily understand, or otherwise I can write it here itself. So for example, if any one of the input of the AND gate is logic 0, for example, something like this, if it is logic 0, I think it's better to take, yeah. So if any one of the input is, if you observe in this particular diagram, if any one of the input is equal to logic 0, for example, something like this, logic 0, logic 0, logic 0, what will be the output? So logic 1, logic 0, logic 0 is logic 0. That means if you write here, if any one of the input of the AND gate is logic 0, the function output is logic 0. It does not depending upon the next input signal, right? Similarly, if you write, if any one of the input of the logic 1, if you apply as an AND gate, what will happen here? You look at here. So logic 1 we are applying here. logic 1 that we are applying here, logic 1 we are applying here. So in the first case, the second input will be the output here. Third case also, the second input will be the output here. Fourth one case also, the second input is your output. So that means whatever the input that you are applying here, whatever the input that you are applying here, that will be considered as an output signal, right? So therefore, this is the information. Let us look at in this particular truth table formation. Let us look at here. So if any one of the input is equal to logic 0, for example, if it is logic 0, for example, what will happen? It does not depending upon the B signal. Outputs I am going to write here in the middle. So the output is 0, 0, 0, 0. Is it clear? So that means that here is a first 0, I have put it there, the output is 0. Next to this value becomes 1. Next to this value becomes x. Now this value becomes, sorry, a value I'm talking about. If a value is equal to, I'm extremely sorry, this is the wrong way that I have written there. I should not write like that. I should write horizontally. If any one of the input is equal to 0, irrespective of the second input signal, the function output is 0, 0, 0, 0. Similarly, if B is equal to 0, irrespective of the second A input signal, the function output is again 0, 0. So that's how. Right. Now what happened if 1 is there? What happened if 1 is there? If 1 is there, so whatever the B input is there, that B input must be translated. B input must be translated. So the B input is equal to logic 1. Okay, B input will be X here. So now forget, just wait for this one. Similarly, if you write in the horizontal vertically at B is equal to 1, it depending upon X signal only. Depending upon X signal only. Okay. And this is also X. So now up to this point, we know it very well. Okay, we don't have any problem. But what happened if one input is equal to 1 and next input is equal to Z? What I'm trying to say is that, suppose you take an AND gate here, one input is equal to 1, another input is equal to Z. So what we are saying that whatever the value that we have, that will be transferred to this one. Okay, but that is not holds good when the input is equal to at high impedance state. So this value becomes unknown only. This value becomes unknown only. That is how that has been framed. Okay, so therefore this value becomes X only. Okay, similarly for every combination other than this X and Z, other than this 0 and 1, so 0, 1, X, everything will be unknown values only. Everything will be unknown values only. Okay, so that means that whatever the combination you take, if input A is equal to 0, for example, the input, another input is equal to also an unknown, then you find an unknown is the output. For example, two inputs are at a high impedance state, two inputs are at high impedance state, there also you can find an unknown value only. So this is the truth table of an AND gate. Okay, so whenever we are simulating an AND gate in Verilog HDL, it follows this truth table and accordingly it will produce an output signal. Clear? So by the way, I want to say a small clarification on this one. What do we mean by logic 0? Okay, logic 0 stands for logic 0 or logic low, or sometimes people will call it as ground also. Okay, what is the logic 1 here? Logic 1 stands for logic 1 stands for logic 1 or logic high or VDD also. And sometimes people will call it as false. People will call it as true value or false value also will be the name. What about X? X means unknown. X means unknown, which means that we don't predict whether it is 0 or it is 1, unknown value. So what do you mean by Z here? It is high impedance state. High impedance state. It is a high impedance state. The resistivity of this one is very, very high. That's what we normally give the logic values for 0, 1, X and Z. Okay, is it clear? So similarly, there are the different gates are also available. I want to show the brief discussion about this one by using different things. For example, I want to show you some two tables of all these things, all the two tables that we should know. Before going to the two tables, it is better to know so we should know this one also. Copy and paste. Okay, so this is actually the notation of your digital gates related input output behavior or input outputs, how many number of inputs that we can take, how many number of outputs that we can take, all these things will be available in this one, gate details. So you can see clearly, you can observe very clearly that AND gate. So actually these are not, whenever you are using these things in your Verilog, it should not, for the AND gate, we have to use small letters only. G1 is the name of the gate, G1, GA, GR, these are all our names only. You can give any name, it doesn't matter, GA only you have to use, no need to use that one, okay? And it very essential is that only single output, okay, output is only single output. Normally they have used a small O, but you don't use O. O means output, don't use O, but you have to use another name because Verilog is a case sensitive. As we know that Verilog is case sensitive. So that means when you are, for example, your intention is small o you have written. Okay. Unfortunately, when you're writing a programs, we are writing the big O. So we cannot define whether it is a big O or a small o. And the visualization is very difficult. Okay. For example, for example, a small rasya, then it's capital A I have written. Therefore, I'm able to visualize that small a and capital A very easily. Right. The point is clear. Okay. So therefore, instead of writing Volvo, we can write it. For any all other gates, we can write only single output and number of inputs can be applied. Whereas the buffer and NOT gate, the outputs can be n number, but input must be a single input. We have to apply. Clear? Now, let us consider what are the different truth tables. So what are the different truth tables that are available for each and every gate? Okay, in terms of, I have given in the previously, I have explained how do we fill the truth table. So the same truth table I'm going to write again here. You please note that one. So these are the gates. Okay. So it is an AND gate. So here I have written this is an AND gate. I have filled how we can do this thing. Okay. If this is a one input, this is another input. Okay. And how do we fill all these things? Similarly, here let us consider for the XNOR gate, sorry, OR gate. For the OR gate, just a brief discussion. For the OR gate, if you apply any one of the input is equal to logic 1, the output will be logic 1. If an OR gate, if any one of the input is equal to logic 0, it depending upon the other input signal, that depending upon that one, it will produce an output signal. That's what it shows here. So that's what it shows here. So if any one of the input is equal to 1, it produces logic 1s here. Okay, it produces logic 1s here. If any one of the input is equal to logic 1, it produces the logic 1 as an output signal. For all other cases, next. If you consider if any one of the input is equal to logic 0, it depending upon the what is the other input signal. This is the input signal. It has to copy it here. It has to copy it here. But the last one must be unknown value only. It's not Z. Don't forget to write that one. Similarly, in this vertical notation also the same thing. If one input is equal to 0, it depending upon this input signal. Okay, this input signal is transferred here, but except last one. Last one, if it is Z, it must be X only. The remaining all other cases unknown values only. Okay, similarly, we have to consider for NAND gate. Okay, for example, if you consider a NAND gate, for example, NAND gate, if you take the two tables, a simple two table for the NAND gate, you can observe that if any one of the input is equal to logic 1, the function output is equal to logic 1. Okay, if any one of the input of the NAND gate is equal to logic 1, for example, it depending upon the next input, whether what is the next input it is. Okay, so in that situation, we can write here, if any one of the input is equal to logic 0, all these signals are output is logic 1, irrespective of the any other input signal. Similarly, at the first case also, if any one of the input is equal to logic 0, it does not depending upon the input number 1, but all the outputs are logic 1. Okay, so similarly, if logic 1 is the input signal here, it's depending upon the complementation will be the output. So, okay, whatever may be X here, if you're writing, you can here is X bar will be the output that you will get. Okay, that's what we can see. Okay, if one input of this one is equal to logic 1, for example, logic 1, other input is equal to logic 0. Therefore, it will be the complement of the next one. It is a complement of the next one. Okay, for all other things is unknown values only. Okay, can you check this one? Okay, for the not similar to the NOT gate, similar to the XOR, similar to the XNOR also will be the possibility in that one only. Okay, please look at the diagram. Then, if you find any kind of problem, so you please ask me the doubts. Okay, so it is a self-explanatory. Whatever the gate activity or whatever the functionality of the gate that is defined in the library is as it is like this only. Okay, its behavior is mentioned in this way, and whenever we are using the gate, and it will take the responses from this one, and it will produce as an output signal. Right. So these are the possible gates we can see in Verilog HDL. Right. Now, similar to this one, we can have another important gates are also available. Those are called tri-state gates. Next one is tri-state. Okay, so we have another possibility of gates are also there in Verilog HDL. Those are called tri-state gates. Okay, only two type of tri-state gates we have in our literature. One is called buff. The next one is called NOT. Okay, buff and NOT we can use in Verilog HDL. Okay, so buff and NOT we can use as a basic gates. Okay, we can use here is the basic gate. You can see here. I have written here somewhere else. Okay, buff and NOT we have used as a basic gates, but here it is not actually directly buff and if. Okay, so instead we went to write it as buff if 0, or I can say that first I want to draw the diagram, therefore you can understand. Buffer means something like this. We have an input signal, we have an output signal. NOT gate means just we have to know that we have to use one bubble there. Here we have an input, here we have an output. So in generally, these gates are just normal gates only. For the small normal gates, it is called buff. We can write input. I can write the name of the gate is equal to G1. I can write G1. I can write. First, I need to write output. Okay, n number of outputs can be possible, but only one input. Okay, but usually for single notation I'm writing. That means only having only single output I'm considering. Okay, similar to that of buffer, we have another one that is called NOT gate. It is NOT. This is G2. Okay, so we will write an output is output and as well as input. Everybody knows this one. Okay. Now, how these things are treated as a tri-state buffers? Then the diagram will be changed something like this. So we have to use extra signal is called control signal. We have to use a control signal. So therefore, by using the control signal, we are defining the output. So in this particular case, the output is defined as whenever we have an input signal. So whenever we have an input signal, the output will be defined immediately after that, immediately by applying the input signal. Okay, the output is defined in the normal gates. The output is defined instantly to the input changes. But whereas tri-state buffers are not like that. Okay, so even if you are applying any kind of changes at the input, cannot be considered as an output signal unless otherwise the control signal is active. Okay, if the control signal is active, then only the changes of the input will be transferred to an output signal. So these are called tri-state gates. Okay, the output will be either the logic 0 or logic 1, or it may be high impedance state at a known value or high impedance state. These are the two things will be there. Okay, so let us discuss about more details on this one. What will happen? Let us write a control signal here, something like this. For example, if the control is equal to, it is equal to 0, which means that the control signal is off. If the control signal is equal to 0, which means that the signal is off. In this situation, what will happen? In this situation, the output is equal to high impedance state. The output will be in high impedance state. You have to remember very carefully this point. When the control signal is equal to 0, the output will be not unknown. It is a high impedance state. That means it's a floating output. It does not have, we cannot define the output. Okay. So what about the next one? If the control signal is equal to, if the control signal is equal to logic 1, which means that it is on. What it says that? It says that output is equal to input. Therefore, whatever the input that we are applying, that will be transferred to an output signal. Is it right? So that's what we have to observe. Similar to this one, for example, you take another tri-state buffer, that is tri-state gate, that is actually NOT gate. Okay, so we are writing as a control signal. Control. Okay, here what will happen here? The same thing is happening here also. What is happening here? If the control is equal to logic 1, logic 0, for example, which means that this is an off signal. What it says that the output value is equal to high impedance state. What about the control signal is at logic 1, or I can say that on, for example. Then it says that the output signal is equal to, output is the complement of the input. Whatever the input we take, it is the complement of the input. Okay, normal NOT operation will be performed if the control signal is on. Okay, if the control signal is equal to off, high impedance state can be seen. Now, this kind of behavior, we want to write it in Verilog. Okay, how do we do this one? So for that one, no need to write a special program for this one. We have a provision of using the keyword called, in this particular case, buff if 1. Okay, buff if 1 is the keyword. It's better to write in the keyword in the form of purple color. Buff if 1. Okay, so this is the keyword that we have to use. The moment if you are using this keyword, the simulator will understand that it's a tri-state gate. Okay, so what is the syntax for this one? That's we should know. The syntax for this one is the name of the gate is equal to C1. Okay, first I need to write an output signal. Okay, next we have to write the input signal. Then we have to write control signal. Then we have to write control signal. So this is how we need to write. I hope people are understanding this one. Okay. Similarly, if you write here, so this is what very important one that we need to write in the tri-state buffers. Similarly, if you write here is a sorry, it's not buffer for the NOT gate, we have to use not if 1, not if 1. So if not if 1 is there, this name is G1, for example, I need to write output first and then input I need to write, and control signal is the last thing that I need to write, right? So this is what we need to write in Verilog if you want to use the tri-state buffers. So another flavor is also there. Another flavor is also there. For example, I'll write here. For example, we have another gates are also there. For example, you can write it in this way. So this is called buff if 0. That means whenever you are applying the logic 0, which means that this gate is on, whatever the input is there, that input will go as an output signal. As an input signal will go as an output signal. Right? I hope you can understand this point. Okay. Next, similar to this one, we take another gate that is called NOT gate, but NOT of the input is possible only if the control signal is at logic 0. Okay, so if it is logic 0 is there, then only the input will be complement to the output will be the complement of the input only. Okay, if it is logic 1, for example, you consider if it is a logic 1, for example, it is a logic 1, for example, then what will happen? The output will be high impedance state. The output will be high impedance state. Similarly here, if it is logic 1 here, for example, then the output will be high impedance state. Right? So therefore, these are the things that I need to consider. Of course, I need to write here is not if 0. Okay, so these are the available gates that we can see in the tri-state concept. Okay, what are the things? Let us conclude now. Buff, comma, not or basic gates. It's not tri-state gates, but the tri-state gates are buff if logic 0, buff if logic 1, not if logic 0, not if logic 1, right? So these are the available tri-state gates we can see in Verilog. Don't forget. Okay, so let us consider the truth table for this one. Okay, so let us draw the truth tables. I have taken from the textbook. Okay, so these are the these are the truth tables that we can see there. Okay, so it is also, you can understand very clearly, for a simple buffer, we have only one input. We have, if the one input, if you apply 0, 1, XX, for NOT gate also complement of the input will be there, and unknown XX. So it's very important to note that. So very important to note that. Note. If you're using the basic gates, output can be either at logic 0 or logic 1 or logic X, but cannot be high impedance state. So very important to note that. Okay, the basic gates, the output can be logic 0, logic 1 or unknown, but it cannot be high impedance state. Whereas the tri-state buffers, it's not like that. Okay, the output for the tri-state buffers, you note that output can be okay, logic 0, logic 1, logic X, logic Z also. Please remember. So for the tri-state buffers, for the tri-state buffers, tri-state buffer, sorry, tri-state gates, not buffers, tri-state gates we can call it as. Here the basic gates. Don't forget this point, okay? And one point, another point that we can understand from this tri-state gates, you can see here. If it is a logic 0, as I mentioned that, if the control signal is equal to logic 0 for buff if 0, so if you see here, it's a buff if 0. Buff if 0 means when 0 is the control signal, it has to transfer the whatever the input is there as an output signal. So here my inputs are this one. So all these things will be considered as an output signals. Okay. So therefore 0 means 0 transferred, 1 means 1 transfer, X means X transfer, Z means X transfer. See, please remember. So here is Z means X transfer. Okay, here also we can see that Z is X transfer. Of course, obviously, it is simply a gate. Okay, therefore, the value it will be considered as X. Now you can see here, logic 0 if you apply. If you apply logic, control signal is 1, which means that for buff if 0, it will be a high impedance state, it will show you that. Okay, therefore, all these gates are logic 0, high impedance state only. Okay, so it does not depending upon the input signals, it's directly it is a high impedance state only. Similarly, if you consider X, so here you have to understand very carefully. Okay, just within 1 minute I will complete it. For example, buff if 0, this one. So for if it is logic 1, logic 0 does not have problem, we have already done. But what about if it is X? Okay, if this is X, it will be logic 0 or it will be logic 1. Okay, that means we cannot define whether correctly we cannot define logic 0 or logic 1 another, but anything will be there. Logic 0 and logic 1 can be there. So in that situation, if the input is equal to logic 0, what you will get the output? The output we will get L value. So I will tell you what is the L value. Similarly, if you are applying the logic 1 here, logic 1 if you are applying, so you will get logic high value. So you will get a high value, something like this. So similarly, if you apply in the logic X here, there is a possibility, and X we don't have any problem. X will be X. If Z aithe emotundi, X avutundi. X it will be. So what do you mean by L? L stands for it may be a logic 0 or it may be Z. It can be anything. We cannot define whether it is 0 or high impedance state. Similarly, if you are using the logic high, H stands for it may be a logic 1 or it may be Z value. We don't know. Something will be happening there. Clear? So that is what we can see about the logical tri-state buffers. So therefore, you can understand, please take these two tables and you can identify how we are getting the values of this one. But anyway, these are the predefined truth tables that is available in the library, Verilog library. And whenever we are using these gates, it will take the outputs from this one and it will show you as an output signals, right? So with this, we have come to the end of the session. We will see in the remaining things in the next class. Thank you.